to the first webinar of our new Student Spotlight series in partnership with the Atlantic Salmon Research Joint Venture. Each session in this new special series will highlight emerging students and research in the world of Atlantic salmon, showcasing the next generation of conservation leaders. My name is Krista Milbury. I am with the Foundation for Conservation of Atlantic Salmon, and I'm happy to be hosting today's webinar. If you wish to use translation today, please navigate to the chat where you will find instructions on how to connect to the AI translation that we have available. For today's webinar, we are very pleased to be hosting Ilyas Hani. Ilyas is a postdoctoral researcher at the Institut National de la Recherche Scientifique. His work focuses on modeling hydrologic conditions and stream temperature dynamics in Atlantic salmon rivers. During his master's degree, he developed machine learning models to estimate thermal refuge areas at main stem tributary confluences. During his PhD, he advanced riverine heatwave modeling and the analysis of compound hydrothermal extremes, integrating climate change and climate variability drivers to better understand and anticipate risk. His work has already proven valuable to many researchers across Eastern Canada, and he looks forward to expanding these collaborations and contributing further to science-based river management and Atlantic salmon conservation. Today, Ilyas will be speaking on riverine heatwave and hydrothermal extremes under climate change and variability. After this afternoon's presentation, we will be opening the floor to questions and answers, and I will now turn the webinar over to Ilyas.
Bonjour, hi everyone. Thank you, Kristen, for this presentation. So today I'm going to be presenting some of the results of my doctoral research, where I focused on modeling hydrological and water temperature condition in Atlantic salmon rivers. Today I'm going to be more focused on the riverine heat waves and the compound or joint extreme events of high elevated water temperature and low discharge condition. So here is a map that shows the Atlantic salmon conservation statute across Eastern Canada and USA. And we can see that the situation is really alarming for most of the provinces of Canada and US states, specifically Quebec, New Brunswick, Nova Scotia, and Maine in the US, where the situation is going from vulnerable to endangered. And so we focused our research on the eastern part of US and Canada as it's shown in this map. Most of this situation is due to elevated water temperature in summer, low flows or drought conditions, and also these extreme events known as heat waves. So the elevated trends in water temperature are well documented through Eastern Canada and US, but we don't know much about what's going on in terms of heat waves in rivers. Heat waves are increasing in different ecosystems. We can find a lot of literature on atmosphere heat wave, ocean heat wave, coastal and lakes. But in rivers, we don't know what's going on. We don't have like a trend analysis or a general view in a climate change and a warming world. So in all this previous research, a heat wave is defined independently of the ecosystems, is defined as the average daily water temperature above a high percentile, which is mostly the 90th percentile of a reference period, which is the 1980-2010 period, for 5 consecutive days with a 3 days allowable gap. These 3 days allowable gap mean that if we have 2 events that are separated by less than 3 days, so we consider them as a single event. And here for more visual, so we have on the x-axis the daily time step. On the y-axis, we have the average water temperature, which is the black curve. The climatology, which is the 1980-2010 moving average window, it's in blue, and the 90 percentile threshold, it's in green. So in red here, we have the heat wave events, which are characterized by the frequency, which is the total number that we have during a year or a summer, the duration, which is the consecutive days where the temperature exceeds this high threshold, and the intensity, which is the event magnitude relative to this specific threshold in degrees Celsius. So recent studies shows that there is an increase in trends in riverine heat waves characteristic. These are few studies that are starting to emerge, specifically in US and Poland in Europe. But last week I came across this new study which which did an amazing work about global heat waves assessments. They considered more than 800 rivers, and it shows that for specific characteristics, for the average duration here in these plots, the average intensity and the frequency for the cold region, which we are interested in, the average intensity is growing at higher rates compared to the other region of the world, as we can see here with the light blue. So specifically for the average intensity, for the duration and the frequency, the situation is less alarming compared to other region, but it's still interesting to see that the cold region will have the most increase in intensity. So for another study, which is focused across the US, led by the team of Tasson, which they studied the riverine heat waves across the whole US. But here I'm going to present the result for the northeast region of the US, which is most close to our Canadian watershed, eastern watershed, and also where the salmon can thrive at the southernmost latitude. So they showed that in terms of frequency, the trends are increasing in the considered rivers, which much less the case for the duration and intensity. But again, the considered stations were located mostly in the southern region of the northeast region. So we don't have much information about the main province states, and I think this is mainly due to the length of the time series. So the length of the time series in the main are short, so we cannot do this kind of trend analysis where we can assess its increasing or decreasing trends. So this is mainly the problematic also in Eastern Canada, where the quality of water temperature suffers from limited number of years of measurements. So here is a map from the RivTemp database that shows the length of the time series for each water temperature station. And we can see that most of the stations have less than 10 years of data, which make it complicated to assess long-term trends and long-term trend analysis. So there is recent studies that try to fill the gaps of the non-continuous time series by estimating water temperature in these non-completed data sets, as the left plot here shows. So in black, we have the observed time series, and we have a machine learning model that came to fill the gaps here in red. We have also some recent study that focused on developing regional models. So basically to try to transfer the information from stations and watershed where we have water temperature information to stations to watershed where we don't have data in terms of water temperature. We can call them ungauged watershed, but ungauged in terms of water temperature, not discharge. So in my first chapter of my PhD, I developed a regional approach for estimating water temperature using a deterministic model and some machine learning approach in Eastern Canada and the US. While we're doing this process, we generated historical daily mean discharge and water temperature time series at a daily time step for the 1979-2020 period. So we considered 35 water temperature stations where we have at least 2 months or 3 years of continuous water temperature data. Here, the size of the circle simply represent the width of the channel at the temperature station. Our smallest watershed was the Bear River in Prince Edward Island, and our biggest watershed and also channel width was the Omelez River in the Ungava Bay. We also had three important Atlantic salmon rivers in the main states. And yeah, it's important also to mention that all these rivers are uh, near pristine rivers, so no big dams and less anthropogenic uh, impacts. So we used a deterministic model to generate those historical continuous time series. So we use SECO. So SECO is a deterministic, conceptual, and semi-distributed model. So it started by discretizing the watershed into squares, what we call whole squares, and each squares can be subdivided to a maximum of 4 partial squares depending on the watershed divides. And this is what it looked like. So here, for example, for the Omelez River, we discretize the watershed. We have the red dots showing the water temperature stations, and the blue color showing the drained area, and in the same time showing the stream network. So SECO started by computing a production function, which basically a water balance that computes water vertically through different reservoirs. It includes the total precipitations, the loss by evapotranspiration, and the amount of water stored in each the soil and the water table. So once we have this volume of water computed for each square, we use a transfer function to route the water downstream. Once we have this volume of water available everywhere in the watershed, water temperature is computed as the ratio of the enthalpy by the volume of this computer water times the specific heat capacity. So the unknown here in this equation, it's this enthalpy, which is the sum of the radiative flux and the advective flux that aren't shown here in this figure. So the radiative flux are shown here in the light blue color, and the advective flux responsible for the transport of water are shown here in the dark blue arrows. So SECO needs meteorological data. So for the historical period 1997-2020, for which we generated and calibrated our model, we used the ERA5 reanalysis data. We used it at the at the daily time step. Here the figure shows monthly because it's just the figures, but we calibrated our model for daily time step. And the resolution of ERA5 is 0.25 degree, which is approximately 30 kilometers square. And also for the future projections, we use the CMIP6, the global climate models from the CMIP6 projects. We selected 6 global climate model with different resolutions. And so we downscaled those models to the ERA5 resolution, and we did some bias correction. And we considered the 2 most pessimistic scenarios, which are here the socio-shared pathway 3 and socio-shared pathway 5, that are showing really the most pessimistic model to see what we can expect if we're not doing much in terms of climate change resilience. So for the results, so once we computed those daily average water temperature time series from 1997 to 2000, but to the end of the century, we considered a heat wave definition as it's proposed in the literature, considered the average water temperature above the 90 percentile for the 1980-2010 period for 5 consecutive days with a 3-day allowable gap. And we computed the historical period average across whole rivers for average intensity, average duration, and total annual duration. And we compared it with the most pessimistic scenarios for the latest period of the future, so 2061 2100. And what we notice here, it's The average intensity, for example, for the historical period, it's gonna go from 1.4 degrees Celsius to 3.25. But the worst here, it's also for the average duration, where we're jumping from 5 days to nearly 60 days, considered always the pessimistic scenario, which is at time 12. And for the total annual duration, we're going for 8 days, considering this same definition, to 100 days, which shows that some of the river gonna enter what we call a permanent state of heat waves. So this is pretty alarming. And here the plots that just show the information for also the whole period. And we can see that in black here, the historical period for the average intensity, we're around 1 and 2 in average. But for the future period, we're going for intensity around 4 and 3, depending on which climate scenario we're using. So those are the results for the temporal trends. For the spatial trends, considered our 35 water temperature stations. So here we notice that for the average intensity, the southern region and also the Baie des Chaleurs and Côte Nord of Quebec gonna experience the most increase in intensity. And this is the same for the average duration, but it's mostly again for the Côte Nord and the Gaspésie region, and the same for the total duration. This is mainly due, in our opinion, to the change in the regime of precipitation. So maybe we're going to have less and less discharge, so which means that the water temperature going to be more extended and elevated, and the heat wave going to be more severe. We didn't expect to have this region more intensified than the southern region, but this is maybe due to the definition of the heat wave, considering the average water temperature. So maybe if we use the maximum water temperature, the result could be different. But this is a good overview of what the region is expecting. So then, when Valérie Ouellet from the Atlantic Salmon Federation show my second paper, which I just described for the riverine heat waves using the average water temperature, she suggested why we don't look at the heat waves from extreme water temperature point of view, so maximum and minimum water temperature. So again, we don't have long time series for this extreme water temperature. So what we did, we calibrate SECO, the deterministic model, for maximum and minimum water temperature. And we did trend analysis using Mann-Kendall non-parametric tests. And we used another test, which is more precise, which is trend-free pre-whitening Mann-Kendall. And here we present the results for some rivers. So for example, for the Moisy River and the Miramichi River, the results showed that the minimum water temperature is warming at a faster rate than the maximum water temperature. And this is the result with both tests. So basically it means that the water temperature at night gonna be warming faster than the day temperature. And this is what we call in atmospheric studies asymmetric warming, where the night temperature are warming faster. It's not the case for the Dartmouth River, which the maximum water temperature is going to be warming faster. For the Sainte Marguerite and Ristigouche, the results are not that significant. So the bold character here shows the significance of the results at the 5% level. So what we decide to do, it's also to look at the spatial trends of these fast warming of minimum and maximum water temperature. So here, the black contour of the partial squares shows that the warming is significant. And we can notice here that for the minimum water temperature, the warming is significant for mainly the whole main channel until a high latitude of the Moisy River. So this is the Moisy River. While for the maximum water temperature, the warming is significant for mainly upstream, but still in the main channel and more upstream here. So the warming is going to be more significant even spatially and not only from a temporal point of view. So what we did with Valerie, it's we redefined the heat wave, considered a new definition, which consider the maximum and the minimum water temperature. So a heat wave is defined when the maximum water temperature is above the 80 percentile for 3 consecutive days. So instead of taking these 5, we went more restrictive, 3 consecutive days with only 1 day allowable gap. And we also considered a flat threshold for the minimum water temperature. So we considered a threshold of 18 degrees for 2 consecutive days. This threshold was considered because of the anglin closure threshold. It depends. Sometimes it's 18, sometimes it's 20 degrees. So we selected 18 since later we did some frequency analysis. And to do a frequency analysis, we need a lot of events. So by considering a lower threshold, we could have more events for a more uh, significant analysis later. So here, the plot shows these the heat waves events with the new definition, and we have only 3 events now compared to 5 in the previous plots. And also, we have less events because the definition is more restrictive than the average water temperature definition. So I developed a Shiny app application through Air where we can select any watershed among the one we studied and select a partial square. So here, for example, if we select the partial square number 271, we can have an overview of the mean intensity, max intensity, all different characteristics of heat waves during the historical period. So those are averaged here during the whole 1979-2025. So I updated my data until 2025 because the papers were included until 2020. And yeah, we can select different time series metric. We can color the map with different characteristics. And this is using the refined definition of heat waves. So this can be helpful for manager if they want to have an idea of where part of the watershed is more vulnerable. And yeah, so that's for this Shiny app. So now for the modeling of these river heat waves. So we saw that there is an increase in trends in different characteristics, duration, frequency, intensity. But if we want to model and predict the return period, for example, of these events in a probabilistic frequency point of view, so we did a frequency analysis, which consists in extracting the extreme of interest annually. So extract the total number of frequency, the average annual duration, the maximum intensity. Then we need to fit a distribution function to the extreme of interest, which will represent the probability of non-exceedance. And from there, we estimate the parameter distribution, which are location, scale, and shape parameter. So for the frequency variable, we fit a Poisson distribution. So in blue, we have the observed events, and in orange, we have the fitted distribution. For the duration, we fit a geometric distribution. And for the intensity, we fit a generalized Pareto distribution. This is basically uh, justified by literature and also the behavior of the variables, frequency, duration, and intensity. So then once the distribution is fitted, we can associate a return period with a specific quantile. So using the following equation. So for example, if we're interested in the probability of non-exceedance of 90%, so this is equivalent to the probability of exceedance of 10%. And this is equivalent to an event with a return period of 10 years. So to do a frequency analysis, we need to respect some assumptions. Among these assumptions are the independency. So the independency here is respected by this allowable gap between events. So we did this 1 day or 3 day allowable gap. So just so we have the events to be independent. The homogeneity, it's respected. We did some statistical tests and it was valid. But for the stationarity, which suggests that the mean and the variance, the statistics of the distribution going to be constant over time, we saw that there is obvious trend and significant trends due to climate change. So the stationarity here is not respected. So we cannot basically do a frequency analysis the usual way we were doing it. So we have the climate change components that affect the stationarity, but we also have what we call the climate variability. So the climate variability is described by those large-scale climate oscillations that describe the interaction between atmospheric condition and ocean water temperature. So this behavior, this interaction will affect extreme temperatures at a global scale. So depending, and we quantify this variability through teleconnection indices. So here I present the North Atlantic Oscillation Index, which is known to affect Eastern Canada and US climate. So a teleconnection index can have either a positive or a negative phases. And here we have a time series of monthly phases of the North Atlantic Oscillation. On the right, we have a plot where we have a figure that shows that, for example, when we are in a negative phase of the North Atlantic Oscillation Index, we have warmer winters, milder winters. So these are the January, March 2010 on the left and January, March 1990 on the right. So depending on the phase of the North Atlantic Oscillation, the winters here are different. So we have warmer winter in the positive phase, warmer winter in the negative phase, and cooler winter in the positive phase. And this is the same also for summer. So this oscillation have clearly can be an additional driver in additionally to climate change. There is other climate index that are known to affect the region. We find the Arctic Oscillation Index and the Southern Oscillation Index. For the Southern Oscillation Index, it acts in the Pacific Ocean, and it can create either the El Nino or El Nina condition, which are really known. So El Nino for a negative phase of the SOE, and El Nina for a positive phase of NOE. So a warming Pacific can have a positive or negative warming effects on the Eastern Atlantic summers, and the same for the Arctic Oscillation. So what we did is we developed what we call non-stationary frequency analysis. So instead of just fitting this distribution for the frequency, duration, and intensity, as I explained before, and estimating the parameters, static parameters, which are constants, we developed conditional distribution, where the parameters of this distribution, so here the rate parameter for Poisson, the geometric mean for the geometric distribution, or the scale for the generalized Pareto, we linked those parameters to time-dependent covariates. So we link them to first covariate the temporal trend. So we considered a yearly temporal trend. And the teleconnection indices, we considered several teleconnection indices known to affect summer in Eastern Canada. And for the teleconnection indices, we averaged them over a 3-month periods, and we defined them prior to the heat wave events. So we can use this information as predictors for the coming heat waves. So for example, here, AO refers to the Arctic Oscillation, and ASO refer to the August, September, October, and -1 refer to the previous year. So the previous condition of AO of the previous summer, of the previous year, can help us predict the condition of heat waves in the coming year. So this was the idea of using the teleconnection indices as a driver for climate variability. So the results showed that our non-stationary model systematically outperformed the stationary model. So we compared both of them. We considered that a stationary condition, non-stationary condition, And using the Akaike index criterion, we noticed that the non-stationary one showed a lesser value of AIC, which shows that the performance is better. So here in orange, these are the duration and the maximum intensity defined using the maximum and minimum water temperature in the heat wave definition. And we define the frequency using the average water temperature definition. So we tried different definition to see how which gonna be the dominant signal in the climate variability. And we notice that the choice of the definition of heat waves alters this dominant signal. So for example, when we use the maximum and minimum water temperature in the definition, for the Moisy River, it's the Arctic Oscillation Index that's control the characteristics of heat waves. But when we use the average water temperature in the definition of the heat waves, it's the North Atlantic Oscillation that drive the frequency of heat waves. And we notice also that there is difference in the season. For the average water temperature, it's the March, April, May. But when we use the extreme water temperature definition, it's the August, September, October of the previous year. So those are some interesting results that show that the definition of the heat waves really matter if we want to explain it with climate change and climate variability conditions. Another interesting results, it's for some rivers, just like the Miramichi, the results are enhanced when we add the temporal trend, which is responsible for the climate change component. And this shows that it adds and capture an additional source of change. So the temporal trend here improve the capture of variability. And this was not the case for all the river, but for example, for Miramichi and Ristigouche River, we noticed that these are the same uh, drivers. And so to have a visual of the results, here we estimate, when we fitted our best model, we estimated the quantiles associated with different return period. So here for the frequency, using the average water temperature as a definition of the heat waves, we note, as we said before, it's the North Atlantic Oscillation during the March, April, May, who control the heat waves. So here in x-axis, we have the North Atlantic Oscillation value, which is either negative or positive. And on the y-axis, we have the frequency quantiles. The black dots show the observed frequency during the 1979-2020 period. And the blue and red step functions here show the quantiles referring to the probability of non-exceedance of 50% and 75%, which refer to a return period of 2 years and 4 years. So what we notice here, it's a negative phase of the North Atlantic Oscillation during the spring showed an increased frequency compared to the positive phase of the North Atlantic Oscillation during the spring. Here, the dashed line showed the confidence interval of our model, and we noticed that in the extremes value of the index, we have higher confidence interval, and this is normal because we didn't notice much events in those extreme conditions. So another result, for example, for the Miramichi River, using the maximum and minimum water temperature as definitions for the duration. So as I mentioned before, it's the North Atlantic Oscillation plus the temporal trend. So here the results are a bit different, where we have a 3D step functions that represent the quantile. Here it's represented by this surface. So in the X and Y axis, we have the covariate, which are the temporal trend and the North Atlantic Oscillation. In the Y axis, we have the duration. The blue sticks here show the observed durations. And the step functions, as I mentioned, is the return period of 2 years here. Here, the quantiles referring to return period to 4 years, and here, return period of 10 years. So if we look here at this right plots, we notice, for example, that for the events in 2020, where we have a duration of 50 days using this definition, maximum and minimum water temperature. So these events touch the surface of 10 years return period quantile. So these events refer to a return period of 10 years. So this is how we can use the information in these plots. And for example, if we have the North Atlantic Oscillation value for the year 2025, which we already have for the previous summer, so we can just plot it in this plot, and we can see the expected return period for different quantile. So in a second part, we focused on modeling. We done with the heat waves, and we focused on modeling the elevated water temperature and the corresponding low discharge. So in most studies, and in all the studies that have been done before to our knowledge, elevated water temperature are modeled apart and discharge is modeled apart. So we don't have like a multivariate model. We call it a joint model to model the two variable at the same time. So here is a picture of the Miramichi rivers that shows two consecutive summers during the same day in August. I think it's 2018, where the river conditions are totally different. So what we did is we selected the 6 rivers. So we have the Highland River here on the left, the Dartmouth, the Moisey, the Jupiter, the Restigouche, and the Wilmot River. And we extracted the maximum annual average water temperature here in the red, and the corresponding low flows, annual corresponding low flows in the blue. So once we extracted those time series, we try to do a multivariate approach to model these two events in a joint manner. So what we did first is to assess the trends of water temperature and discharge using a univariate Mann-Kendall. So we showed that for some rivers, the trend is significant in water temperature. For other rivers, the trend is significant in discharge. But also we did a multivariate trend, which consider both variable at the same time. So we used the CIT and CET model tests. And this shows that the trends are significant across the whole considered rivers. So we need to use a multivariate approach, or what we call a multivariate frequency analysis, instead of modeling each variable apart. So here the trends are really obvious from a mean or location parameter point of view. So what we did also is try to see what's going on if we include the climate variability information. So here we present the L moment ratio diagram, which basically are plots that help us either to select the best distribution for a variable, or to have an overview of the statistics of the distribution. So on the x-axis, we have the L skewness, or the skewness, which describe the symmetry of the distribution. And on the y-axis, we have the LCV, which is equivalent to the CV, or coefficient of variation, and will be describing the variability of our time series. So here for the Restigouche and Wilmot, we're showing the result for the low discharge. So here each point, colored point, showed the 21-year moving average of the low discharge time series. And the colors refer to the value of the North Atlantic Oscillation with an average mean. So the interesting thing here is we notice that when the North Atlantic Oscillation Index is high, we have low variability in discharge, and inversely, when the North Atlantic Oscillation Index is low, we have higher variability. So we notice the same for the Wilmot River, and also for the Skewness. We notice that the temporal trend, the more we advance in years, we have the Skewness is increasing, while in here it's decreasing. So those are important insight that we cannot uh, assess just from a simple trend test or a simple time series plot. So it gives us additional information of what are the responsible drivers in variability, and this is important to include in our studies. So we developed a bivariate because we have two variables here, so it's still a multivariate frequency analysis. So the steps are just as we did for the frequency analysis for the heat waves. It's pretty much similar. So we fit a distribution for the water temperature maximum time series, and we fit a distribution for the corresponding low flows. So once the best fitted distribution is selected for both, we need to model the dependent structure of these two variables. And here we use the copula, which is a mathematical function that will links this these two marginals, and it has its own parameter theta here. So by combining the marginals and the copula, we can have what we call a joint probability density function that will allow us to estimate quantile for a return period for joint event and not separately. And again, the non-stationarity here, the stationarity is not applied as we showed with the climate variability plots, the colored plot I just saw before, the trends that are really clear. So we linked the parameters of the copula and of the marginals to teleconnection indices and temporal trends. So here I'm going to present the results. So again, the joint non-stationary model outperform the independent non-stationary model. So the independent here I refer to if we model water temperature alone, discharge alone, accounting for non-stationarity, and if we model the both variable at the same time, accounting with non-stationarity. So the performance were clearly superior for the joint non-stationary model. So here I present the result for the Ristigouche. So for the Ristigouche river, the best copula fitted is the Joe copula. So this is like we have name for distribution, univariate distribution. We have also names, different name for copula. So the Joe copula rotated by 90 degrees. So this 90 degrees, it's to capture the negative dependency between elevated water temperature and low discharge. So here the dependence is negative, so we need to do a rotation of 90 degrees. For the water temperature, the best marginal fitted was the Weibull. For the best fitted distribution for the discharge, it was the log normal. For the water temperature, the location parameter showed the best performance. So the best performance was shown when the location parameter is linked to the temporal trend, while the scale parameter is kept constant. But for the discharge, the best model was when the location and the scale parameter were linked to the North Atlantic Oscillation Index, while the copula parameter theta here showed the best performance when it's kept constant. So this is what the results look like. So here are what we call the bivariate quantile curves. Here we show the probability of non-exceedance of 75%. So this is representing a return period of 4 years. So on the x-axis, we have the water, on the x-axis, we have the water temperatures quantile. On the y-axis, we have the discharge. And because of the dimensionality of our models, we need to fix some variables. So we fix the North Atlantic Oscillation Index to a 0.6, a positive phase, and we fixed it in another case to a negative phase of 0.2. So what we notice here, as we said, the water temperature is dependent on the time here, as you can see. So you see that the curves represent the time are moving to the right. So the quantiles are growing, the water temperature going from 24 degrees to the 26. If we were in stationary condition, we will have only one curve. So this is the advantage of non-stationarity, that it shows how the model behaved through times. So the water temperature moved from 23 to 26 in both North Atlantic Oscillation condition. But since the discharge is dependent on the North Atlantic Oscillation, we notice that the variability differ depending on which phase we are located. So when we are in a positive phase, the discharge is below 75 meter cube per second. But when we are in a negative phase, the variability is bigger and it's between 75 and 150 meter cube per second. So from this, we can also compute joint conditional probabilities. So those are some interesting probability we can compute with these models. So for example, if we're interested in the probability of being that the discharge is lower than 60 meter cube per second, knowing that water temperature is above 23. So this plot shows on the x-axis the years for specific summer, and on the y-axis we have the probability of being below the 60 meter cube per second. So the continuous lines show the joint model. So when we model both discharge and water temperature in the same time, and the dashed line shows the independent model. So here we notice that the independent model underestimates this probability across all years. It does a good job, but it misses information. So that's why we have this underestimation. And what we notice also, it's when the North Atlantic Oscillation Index is high, the probability of having discharge lower than 60 meter cube per second is pretty high also. But when the North Atlantic Oscillation Index is low or medium, the probability drops. So those are some interesting uh, insights we can use to try to predict and have an idea of what we're expecting, knowing the North Atlantic Oscillation value. So the takeaway message from this research, it's so first we simulated those long time series for for average daily discharge and water temperature. For now, we're adding rivers, so we are at 42 Atlantic salmon rivers, and this information is available in the reef temp database. Uh, Also, it's important to start collecting water temperature in rivers where Atlantic salmon can potentially migrate in the future. Because I noticed when I was developing the regional model that I've talked about in the beginning, a lot of rivers had no data because there is no salmon. So it will be interesting. Maybe salmon will migrate to those rivers in the future since they will be more adapted in terms of water temperature. So this is an important thing I thought about, and I thought it's worth mentioning. Also, so the long-term trends, the climate change, and the climate variability through these teleconnection indices successfully explain parts of this interannual variability in all heatwave characteristics. And that the seasonal prediction of diverse climatic indices can be used to model heatwave quantiles. So for example, it will help managers uh, uh, to, to, uh, to make the right decision. So for example, we don't manage a river the same way when the North Atlantic Oscillation is positive compared to when it's negative. So those kind of insights can be really helpful in improving the management and of rivers, and also for the joint modeling or the joint events of elevated water temperature and low discharge. It's important to consider them as a multivariate process instead of modeling just the water temperature and we kept the discharge apart. So this was one of the important results we found here, and consider non-stationarity again because things are moving in the climate change direction, but also the climate variability import in this case. So yeah, those are the papers. Three of them are published. One it's under revision that I did in my doctoral research. And yeah, if you have any question, I would be happy to answer. And I want to thank all the partners also that participate in this advancing research of Atlantic salmon. Thank you.
Great. Thank you so much, Ilyas. That was an excellent presentation. So yeah, we can now open the floor to questions. Please raise a little hand on your screen and I'll call on you. And just double check and make sure that you can unmute and you are unmuted for your questions. Yes, so we'll just give everyone a little second. If you have a question, please raise your hand. so far no questions. That means your presentation was excellent, I think, Elias.
Thank you. Yeah. Maybe everything is clear. But yeah, we'll be happy to give comments and answer some questions.
All right. Yeah, so there's no questions coming in. Just give it a couple more seconds here, but if anyone does have any questions or think of anything they want to ask after the presentation, of course, feel free to reach out to Ilias directly or to the foundation, and we'll pass along any messages you have to them. Okay, so I think that's it. I don't see any questions coming in, so that would be it for today's webinar. So we have recorded this session and it will be available on our YouTube page. And our next webinar will be one of the regular FCAS webinars, and it's going to be on February 4th with Dr. Mark Fass from the Atlantic Veterinary College of the University of Prince Edward Island. The title of this webinar will be Harnessing Comparative Genomics and CRISPR for Sea lice Resistance in Atlantic Salmon. So we hope to see you all in that webinar. And also keep an eye on our social media and stay tuned for more of these regular webinars, as well as our new Student Spotlight webinars, which are co-hosted by the ASRJV. So again, big thanks to Ilias, the Atlantic Salmon Research Joint Venture, and to everyone who participated today. Have a great day, everyone.
Thank you, Kristen, and thank you everyone for your presence. Have a great
Bye-bye.
day. Bye.